MCT, we're going to do 3D trig problems today, which I think are a load of fun. But anyways, I grabbed 2 problems out of your book to solve. And I found that the diagram was absolutely essential to come up with the solution. So in order to measure the height of a cliff, AB, a surveyor uses a baseline CD and records the following data. So we have our data drawn and we need to come up with that diagram. So we need a baseline, and that's on the ground. So I'm going to draw CD. So we will CD. He can measure that on the ground, and we have a distance of 240 meters. Okay. He has a cliff he wants to measure of AB. So let's draw our cliff. I'll do that with dotted. So I have my cliff. It's a little bit away from his baseline, and we know some other angles. So on the ground, I'm going to do green for grass. I have a triangle that has been set up on the ground. And what I know is the 240. I also know angle BDC is 55.2. We can measure angles between lines of sight on the ground quite easily. Angle BCD, so the middle letter is the one where we put the marking, is 64.3 degrees, also on the ground. Then we have angle ACB, but that is in a different triangle because it involves point A. So ACB would be the angle at C here, which is a 28-degree angle of elevation. So he had his clinometer and he took a little angle there. We're going to put a little, so I can hope you can see that the green with the black line is on the horizontal and the blue triangles are on the vertical. We can assume the angle between horizontal and vertical is a right angle. So if these would be helpful, we can make little markings of right angles there. And notice that nothing's to scale because it's hard to draw in 3D. So we have all of our data put on the diagram. We want to find the height of the cliff. There. In order to find H, I need to use trig in the blue triangles, the vertical triangles, and I don't have any lengths there. So I'm going to use the green horizontal plane to find some lengths. So I have the 240 already. I could use the 240 and the 64.3 or the 55.2 to find the lengths of either CB or BD. And it doesn't matter which I choose. So I'm going to find the length of C to B in the horizontal plane. I'm going to use that in the vertical plane in a bit to find the height of the cliff. So triangle on the flat plane, I want to find CB, which is the same as a little d. So I have to think, can I use right angle trig? No. I have a triangle with 64.3, 55.2, and a measurement of 240, which leaves me with an angle in the corner of 60.5 degrees. So I can't use right angle trig. I can use the sine law in order to find the side CB. So for the sine law, I am going to use sine d over d equals sine c over c equals sine b over b. And I'm going to fill in my numbers. Sine d is 55.2. Little side d is the one that I want to find, CB. So I'm just going to call it CB. Sine C is 64.3, sine of 64.3. Little c, don't know. Sine B is sine 60.5, and little b is 240. So I always write all three ratios. The middle one, don't know, don't care. So I am going to solve by using the outer two ratios. To get CB by itself and not on the bottom of the ratio, I'm going to cross multiply. So multiplying both sides by 240, I have 240 sine 55.2 on the left now. On the right, I have CB times sine 60.5. And before I touch my calculator, I'm going to divide both sides by sine 60.5. So I'm going to enter 240 times sine 55.2 divided by sine 60.5. I will get 226.4 approximately. Does that make sense looking at the diagram? Yeah, it's a very reasonable answer for CB. Now that I have found side CB, I am going to find the height. And now I'm going to use a triangle in the vertical plane. I am going to use triangle ABC. And I made that choice when I found side CB instead of BD. So in the vertical plane, triangle ABC, this is the height that I want. I have the length from C to B. It is 226.4. And I know the angle in the corner is 28 degrees. So I can use SOHCAHTOA. I have adjacent, I want opposite. So I'm going to use tan. Tan of 28 degrees is the height over 226.4. So I'll multiply both sides by 226.4. The height is approximately 106.3. Page 222, number 15. Two roads intersect at an angle of 38 degrees. Two cars A and B leave the intersection at the same time, but on different roads, but both facing somewhat east. After 2 hours, car A has traveled 140 and car B has traveled 160. At this time, a hot air balloon is directly above the line between the two cars. The balloonist notices that the angle of depression to the faster car, which is 1 kilometer away from the hot air balloon, is 25 degrees. So the hard part in these, honestly, is not the trig, but the diagram. So we have two cars on the road. So they're on roads. They are on the horizontal plane. So I am going to draw their scenario with solid black lines. They were at an intersection together and both traveled on a diagonal road, well, at a road that intersected at an angle of 38 degrees, and they're going somewhat east. So let's do car A like this, and car B like that. And remember, it's in 3D, so it's hard to get the diagram. Okay, like that. That'll do. We know that that road intersects at an angle of 38 degrees. After 2 hours, car A has traveled 140. So this is car A. And this is car B, and he has traveled 160. And this was the corner where they met, so let's call it C. So everything green for grass is on the horizontal plane. At this time, a hot air balloon is directly above the line between the two cars. So the line between the two cars, let's do it dotted. And our balloonist is above that line. So we've got to draw a balloon up above, so way up in the air here. Okay, whatever. So he's up above the line in between them, and the angle of depression to the faster car. Now it appears to me that the faster car is car B, and the distance between the balloon and the faster car is 1 kilometer. And his angle of depression to the faster car. So it's very hard to draw this in 3D, but the guy in the balloon looks horizontally, other words, into the horizon. And then he looks down in a depressed sort of way, angle of depression. Down to that car is 25 degrees. It means that if the balloonist is looking down at car B with an angle of depression of 25 degrees, it happens to be true that the angle of elevation as B looks up at the balloon would also be 25 degrees. That comes from the Z pattern that we looked at before. Our goal in this problem is to find the distance from the hot air balloon to the other car. So our goal is to find this distance right here. Okay. Now remember that balloon is directly overhead of that line. So with 3D problems, you can only work in one plane at a time. So I'm going to work on the horizontal plane because I have two lengths and an angle. And I'm going to use that green information to find the length of AB. AB is also shared with the vertical plane. So I'll use it to find X. So to find length AB, I'm going to look at the horizontal plane triangle ABC. So I have to consider the green triangle, the horizontal plane. Can I use right angle trig? No. Can I use the sine law? No. I have to use the cos law. So I want to find the length of AB. I'm going to set it up because I know angle 38. AB squared equals 140 squared plus 160 squared, and so on. We didn't practice one of these yesterday, so this is a good idea. Okay. AB squared equals 140 squared. 140 squared is 19600 plus 160 squared is 25600 minus these three numbers are glued, sorry, these four things are glued together. So we end up with 2 times 140 times 160 cos 38 is 35302.9-ish. AB squared is, putting those numbers together, 9897.1, and the length of AB itself is the square root of that number. We will get 99.5. Does that make sense if you consider that scenario, that if they've left and 2 hours later they're 99.5, almost 100 kilometers apart, if the road they were traveling on was 38 degrees apart? It's absolutely reasonable. So we now have a measurement that's in the vertical plane. So in the vertical plane, we have the triangle 99.5 with a length of 1 kilometer. So my triangle is way out of proportion. An angle of elevation of 25 degrees, and we want to find that side. I need to think, can I use right angle trig? No. Can I use sine law? No, I cannot. I do not have an angle side pair complete, so I need to use the cos law. So for cos law, I'm going to have x squared equals 99.5 squared plus 1 squared minus 2 times 99.5 times 1 coast 25. Be careful how you type it in. If you want to do it all in one step, you might want to use brackets. I would get x squared equals 9720, 0.89, which leaves me an approximate value for x of 98.6 kilometers. So the helicopter is very much closer to being straight above B and a long ways from A on that road. Let's give you some to try. Page 21, numbers 5 to 13.